So first of all, thanks a lot for inviting me to give this presentation, Kevin and Professor Gregor Renze. And my presentation will be focused on the challenges and perspectives for the effective deployment of AI-based solutions for building energy management. And now, more and more, the AI application will be implemented in a next generation of energy management and information systems, which will include more, services that we can categorize in two different families. Services that are based on energy information systems that are aimed to support the decisions for different stakeholders, from energy manager to final users to aggregator, including services like fault detection, diagnosis, or energy demand prediction or anomaly detection. And another family of this new kind of services that leverage AI are based on automated system optimization that we also discussed today in this workshop, including both model-based and model-free advanced control with predictive and adaptive capabilities that can take into account more than one objective and fully exploit the flexibility of our buildings and to be responsive to demand response signals. However, for a full penetration of AI-based EMIS solution, we need to face and address a number of barriers. I tried here to summarize some of these barriers, like regulatory barriers or economic barriers or organizational barriers or technological and technical barriers. So just a few words about some of them. The complexity in integration. So now we have a lack of standardized protocols, and we have compatibility issues with existing BAC system. Also, we need data for an effective AI training. On the other hand, we also need to take into account on how to integrate our EMIS services in the existing infrastructures. And also we have interoperability issues due to the difficulties in integrating various technological components. But especially I want to focus my attention on high initial costs that are related to the cost that I need to face when I want to train an AI model from scratch that is very well connected with the ongoing expenses that during the operation of building I need to face. And also the uncertainty on the economic benefits related to the application of AI-based energy management and information services. So I here reporting this scratch some of these barriers, because I think on based on my experience and on my research group that if we try to add some key features in the current AI-based EMIS solution, we can partially address some of these barriers. And in particular, I'm referring to the portability and interoperability, to the transferability and to the interpretability. So what I will try to do with this presentation is to discuss these three kinds of features as a way to enhance both the scalability and the usability of this kind of EMIS services that make use of AI. Okay, what about the portability? When we refer to portability, we refer to the ability of a software or systems to be easily implemented from one platform to another or to different locations. And also, it is well connected with the portability, the interoperability that refer to the ability for system, devices, equipment, sensors, or application to connect, communicate, and exchange data across different boundaries and stakeholders. So which is the opportunity that we can pursue through the inclusion of these features in our services, is to allow building owners and operators to implement the same EMIS application in multiple locations or in multiple infrastructures without a significant effort for the reconfiguration or for the development efforts. So which is the solution that can help us to increase the portability and interoperability? For sure, to build consistent semantic metadata models that make use of ontology that can define a unique taxonomy and relationship between entities. Okay, it seems quite simple, this approach, But actually, we have a number of different challenges to face. First, which ontology should we use? As we know, we have a number of different ontologies according to the scale of analysis, from city to building to system. But also, if we use the same ontology, in principle, two different analysts can define two different models for the same building system. So by using different level of detail, this means that a particular application can fail and be executed also if I use the same ontology. And finally, considering that an MIS application can be ideally implemented and deployed at any point of the building life cycle, the key challenge is then to develop a modular application that can be easily integrated in existing blocks along the all the building life cycle. So we are trying to work on that, and in particular, we are working on the opportunity to introduce frameworks that can prove that thanks to a semantic layer, a portable application pipeline can be very helpful to enhance the transferability and portability of a particular application. We are working in particular on our campus, in which we have a very large monitoring infrastructure. This is the case of an application related to an anomaly detection services for a PV system, in which we tried to inject some practical issues along about 8 months of deployment of this portable application pipeline. And in particular, we worked on opportunity that you need to substitute the estimation model that is at the base of the anomaly detection service, or you need to change the deployment strategy. Or also, we are test the opportunity that there is a disconnection of sensors or a changing of naming convention. So we finally realized that the frameworks that make use of a modular structure and also of a semantic layer can be really portable and can be transferred from a PV plant to another PV plant, because we tried this portable application across the 7 different PV plants that are installed in our campus. So now that in some extent we have realized that the semantic layer can help to increase portability and interoperability of an application, the next question is, who is in charge to build the metadata model? So in most of the cases, the data modeler can be different from the application developer. So this means that you can follow 2 different strategies. The first strategy on the left is an application-driven metadata model development. So it means that the semantic model is developed according to the manifest of your application. But you can also follow a different strategy, that is a metadata model-driven relaxation of application requirements. It means that if I have an existing metadata model, I should try to relax my manifest and so my queries in order to obtain a good integration of my application with my existing semantic model and to ensure that it can operate over the building life cycle. The other key features that I mentioned before is the transferability. When we talk about transferability, we refer to the ability of a machine learning-based models to be easily implemented through a knowledge sharing process from a source domain to a target domain, operating also in different operating conditions and also in with different objectives. So which are the practical benefits of the transferability? The opportunity to improve the accuracy of the models, but also to increase the cost efficiency, because I need to lower data and then I can have a quicker and a cheaper deployment process. And the scalability, because thanks to transferability, I can facilitate the deployment of scalable solutions across multiple buildings. So which are the solutions that I can implement for enhancing the transferability of EMIS application is to use transfer and imitation learning frameworks. Here I reported two strategies in which the two frameworks can be used in a sequential mode. So start with the transfer learning to adapt a base model, then refining it using expert demonstration, that is the imitation, or combine features from transfer learning and imitation learning in order to develop robust models. But which problems does the transferability can address in building energy management? For sure, the transferability of data-driven prediction models in relation to different applications, like load prediction, occupancy detection, activity recognition, or building dynamics, or FTD, or also personal comfort system. So the opportunity is to use the transfer knowledge process in order to support the scalability of this kind of application when in the target buildings you have very few monitoring data. The other application is related to the control policy. So the opportunity to transfer a trained control agent from a source to a similar target building in order to speed up the process of the deployment. So we had the opportunity to demonstrate the performance of a transfer learning process when a deep reinforcement learning control was implemented in a building in Zurich in collaboration with ETH, that is the ILO building. So in that case, our aim was to transfer a control policy from an office to another office. So from a source office to a target office, so in two different zones of the same building. And in that case, we used a high-fidelity simulation environment based on Open Modelica for pre-training the deep reinforcement learning controller on the source building. We implemented it on the source office. And then with that knowledge transfer process, we were able to really implement all the knowledge acquired from the source control agent to the target office, obtaining good results. Then, thanks to a digital twin, is based on physics reasoning, we were also able to compare the performance of this transfer learning process with other more traditional control like PI or rule-based control with the same boundary conditions. Here I reported an interesting schema with the infrastructure that include a PLC that is connected with the gateway and the opportunity to use a REST API for connecting our deep reinforcement learning algorithm, and results that we obtained with different traditional control or reactive control, also considering the opportunity of using a deep reinforcement learning from scratch, so without any knowledge shared from the source building in comparison with the process of online transfer learning. We both obtained energy savings and a good control of the indoor temperature. Okay, another opportunity that we are trying to work on is to scale up from a single building scale to a district scale, especially focusing our attention on energy communities. So in that case, the transfer learning process can help a lot to speed up the process of deployment of the control agent, considering the similarities between the buildings of the community, but also you can use the transfer learning frameworks for transfer the knowledge of prediction models that are related to the disturbances or to the building dynamics. In that case, by testing different architecture, centralized or decentralized, we trying to demonstrate how a coordinated energy management of a district of buildings can support a lot the services for the grid, the flexibility services, but also at the same time to minimize the operational cost and to guarantee a good indoor temperature control for each building of the community. Okay, what are the challenges in applying the transfer learning in smart buildings? So on the basis of my experience of my research group, for sure, the selection of the source building is a very key aspect to take into account in order to avoid any negative transfer learning. Then we are trying to introduce new key performance indicators that are tailored for each application that can benefit from the application, from the use of transfer learning process. And as Philip discussed before, the importance of having of defining an high-fidelity digital twin for comparing the performance of transfer learning with more traditional machine learning application. Also about the similarities, you realize that it's a very important aspect, because especially when you have very different systems with a very different objective in your problem formulations and different observation space, the transfer learning can fail. And about the real implementation, a very practical recommendation is to use an observation space that include easy to measure variables to take into account about the privacy issues related to information that you share between source and the target buildings, and to ensure a building safe operation. In that case, we considered sort of backup control during a failed operation of the transfer learning process. The last features, that is the interpretability. When we talk about interpretability, we refer to the extent to which an inference mechanism and output decisions made by AI models can be fully understood by human user. Here, the objective is for sure to increase the stakeholder trustness in adopting the AI-based MIS solution, because as you know, there is a sort of resistance to technological change from different stakeholders. The interpretability features can support the penetration of these kind of services. How? Or by using more simplified data-driven models when possible, that are more interpretable, or also to adding a Excel layer in your pipeline to help explain and interpret AI decision. Here I reported a scratch in which it's clear that the outcome of a Xi layer is not only the final user, the domain expert, can be also the developer of the models, can understand through the Xi layer how to improve the model that is under developing. Indeed, if we think in which stage of analysis can really help the interpretability, for sure, in describing what are the top features of my model, but also it can help in performing what-if analysis, so show how the prediction changes corresponding to the implied change of input. Now, the main challenges to be faced are listed here. So simply adding Xi components does not necessarily can help in enhancing the user performance in tasks like decision-making analysis. So even when you have explanation from a Xi layer, user may struggle to identify errors in the AI reasoning. So what I concluded is that we need to shift from a technocentric approach toward a more human-centered analysis in order to bridge the gap between the algorithm explanation to an approach that is different. It is based on an actionable understanding. Which problem the interpretability can address in building energy management? We test the interpretability in both energy information system services and in automated system optimization. As an example, the integration of an explainable AI can help in further explain the process of fault detection, the analysis based on empirical models, or also explain the output and the learning mechanisms or prediction of an estimation model used for building energy benchmarking or prediction. Or same modules can be used for explaining and interpreting the control policy defined through an advanced control, for example, based on reinforcement learning. This is an example in which I titled this slide is not only a matter of size, because one of the opportunities that we can pursue is to extract rule from an advanced control, having then benefits also for, a more cheaper, more easy integration with less computational cost connected with the implementation of that control. This is the case in which we compare the baseline control according to ASHRAE guidelines with a deep reinforcement learning for a handling unit, and with some very simple if-then rules derived with a regression tree from the control policy obtained with deep reinforcement learning. So finally, we obtained results that are comparable between the rules and deep reinforcement learning, but with a number of benefits related to the integration that becomes more simple and easy to do. Finally, the new frontiers and opportunity for scalability and usability. I think that generative AI and the large language model in the next future will be more and more protagonists in order to enhance the portability, the transferability, and interpretability. About the portability, thanks to LLM, we can develop standardized model of semantic schema with the aim to decrease the complexity, because through simple descriptive prompts, we can finally obtain robust semantic metadata model. About the transferability, we can face the problem of data scarcity, or in general of the privacy issues, to the generation of synthetic data sets from open sources, similar sources of data, but also from high fidelity physics-based simulation models. And also to define archetype of source models that are already trained for particular task. And finally, the interpretability, the LLM can support a lot the explainability of some outcomes of complex models, and also to work as an interactive system where user can ask questions about why a model took particular control decision, and then receiving detailed explanation about all the reasoning path. From European side, just a few words. Very recently, we approved the European Building Performance Directive that finally take at the center the digitalization process as a way to finally obtain the goals of decarbonization. And in particular, has been introduced a very important indicator, that is the smart readiness indicator. This indicator will speed up the energy and technological transition because it leverages on the opportunities that are provided by digitalization and by the connectivity. Indeed, this kind of indicator is based on the opportunity of considering the level of functionality of automation connected to different domains, including cooling, domestic hot water, electricity, dynamic envelope, electrical vehicle charging, on different impact criteria. And among the impact criteria, we need to assess not only the energy saving or the comfort, but also the information to occupants. So how much we are informative about the performance during operation of a building, and how much the level automation of a particular services has impact on the energy flexibility and storage operation. Okay, here I reported some scenarios from European Commission consequent to the implementation of this kind of indicator. Okay, we expect a reduction of CO2 emission, primary energy, but also an increment of net employment created by the introduction of this kind of indicator. I reported here, this is my last slide, just some service connected to the domain heating and cooling, in order to demonstrate how, if you want to really implement a high level of functionality or automation, it's the same. You need to consider a predictive energy management by using machine learning or AI algorithms. Just a few examples. If you take into account the thermal energy storage, and you want to reach the level 3, you need to take into account or considering a storage that is capable to accept a signal from the grid in order to implement demand-side management strategies. Or the service related to the report information, you need to include a forecasting management and also predictive management that take into account of a data-driven fault detection. And finally, the service related to flexibility and the grid interaction, which you can read that is explicitly considered an optimized control of heating system based on local prediction. This means that we expect that in Europe, thanks to this indicator, in the very close future, more and more DI-based services for energy management of buildings will be mandatory to use, because this indicator will be mandatory to be calculated from 2027. So it's the time that we start to think on how the barriers that I try to discuss in this presentation can be really faced and addressed. Thanks a lot for your attention.
All right, thank you so much, Alfonso. I don't know if you could hear, but there was a loud round of applause from the room there. I think much appreciation for your work. I think we'll start with a couple of questions from online. Gregor, do you want to unmute and just ask your questions?
Sure. Can you hear me?
Yes.
Yes, Gregor.
Yeah, Alfonso, you mentioned the term negative transfer learning. Do you mind elaborating?
Yeah. Negative transfer learning means that the performance that you had with your transferred agent control is not performing like an existing control that is trained from scratch in your target building. So this means that finally your transfer learning failed.
Yeah. Thank you. The second question I have, Alfonso, was, could you give examples of explainable AI that that appeared to you as working well, that you could recommend to others who are dealing with the kind of criticism from building operators and the need for greater levels of explainability?
Yeah, so I use the XI layer in both automated system optimization and energy information system. In particular, when you refer to a prediction model, you can really, gain information on which are the input variables that really driven your output, and also to better understand in which region of existence, so your input variable, your model is not working well. Okay, this is one of the opportunities that you have. About the automated system optimization, as I mentioned in my presentation, with the extraction of if-then rules from an advanced control, we are realizing that it's an opportunity to continue to explore, because in that case, it's like an explainability layer, because if-then rules are very, transparent to be understood from a user. So I recommend in these two particular cases to use XI layer.
A comment on this use of rule extraction that you showed. From my own experience, there was always great hope for the extracted rules using a tree-based method, for example, to be more portable and to apply more broadly. It turned out, unfortunately, that the transferability of the rules, the extracted rules, even though they were more interpretable, they didn't transfer well to other buildings.
I completely agree.
It's just an experience I had.
Yes, Gregor.
It's unfortunate.
Yeah, unfortunately, thanks a lot for this comment. Yes, are very tailored, that decision tree to particular building. But we are trying to assessing which are the benefits in terms of implementation and integration. Okay, so if you use a model for training your advanced control and then derive rules that can be more easily integrated, maybe it could be a way to continue to explore.
Absolutely. No, I think that's the right direction. That is the right direction.
Thank
Thank
you.
you, Alfonso.
Thank you, Gregor.
All right, great discussion. Do we have one quick question from the room? Okay, I guess not. So then in the interest of time, I think we will move on to our next speaker. And thank you again, Alfonso, for a wonderful presentation.